Hello and welcome. My name is Jess Speedie, and I'm a graduate student at the University of Victoria in British Columbia, Canada, supervised by Rubing Dong. The work I'm presenting today, though, was done during my time at McMaster University, supervised by Ralph Pudritz, and in collaboration with Alex Cridland. This talk serves as an advertisement for our to-be submitted paper, so please reach out if you have any comments or suggestions. Ever since the ALMA Partnership Brogan et al. 2015 release of the first high angular resolution observations of HL tau showing gaps and rings in the dust component of the disk, the question has been, what is responsible? One of the proposed explanations is the so-called planet-disk interactions interpretation, the idea that gaps in the dust distribution are opened by planets orbiting there. Many works have successfully carried out hydrodynamic simulations to determine the right planet masses and orbital radii that would recreate the pattern of gaps and rings that we observe in HL tau. Usually a planet is placed in the location of a gap. So we know that planets can open dust gaps. But to understand the full story, we need to connect our hydro simulations to the entire process of planet formation. We need an explanation for how a planet of the right mass and semi-major axis came to be there. So how can we form dust gap opening planets with large semi-major axes, by which I mean out at tens of AU? Planet growth and planet formation are tightly intertwined, and as the results of the work that I'm presenting to you today stress, planet growth and migration also depend on their natal disk's viscosity. So a little background on viscosity. Current planet formation theories assume that protoplanetary disks evolve under the influence of an effective viscosity, which we are attributing mainly to the magnetorotational instability MRI. This viscosity is what transports angular momentum outward, allowing most of the disk mass to move inward and accrete onto the star. Following the Shakura and Soniev prescription, we express the viscosity, nu, as alpha, which is just some unknown number, times Cs, the isothermal speed of sound, times h, the gas scale height. By changing the alpha parameter, we change the viscosity. And the viscosity is crucial to how the disk evolves, but it also has important consequences for planet formation. Historically, in conventional viscous disk models, there are barriers to forming planets at large orbital radii. Firstly, radial drift can quickly deplete the outer regions of the disk of any planet-building material. Secondly, the torque balance on these low-mass planetary embryos tends to drive them inwards to small disk radii, and the rate of inward migration can be very rapid, on the order of 10 to the 5 years, which is short compared to the disk's lifetime. This is the well-known type 1 migration problem. So in our work, we explore how planets can overcome these two barriers and reach substantial masses out at large orbital radii if the disk viscosity is lower than typically assumed. And we note that a low viscosity is the direction that the observations are maybe currently heading. And I list here some examples. So we present semi-analytic planet formation simulations based on a detailed disk astrochemistry model. In our disks, we've adopted the conditions in the HL tau protoplanetary disk, as well as a set of gas disk masses that bracket the observational constraints. We grow and evolve 100 planetary embryos, each in their own separate simulation, with initial orbital radii distributed throughout the disk over the course of roughly 2 million years. The planets grow by core accretion, and they migrate according to self-consistent calculations of disk torques. So our code allows for an accurate calculation of the thermal, density, and entropy gradients that are involved in computing the mass-dependent disk torques that determine planet migration. We do all of this for two different values of alpha, 10 to the minus 3 and 10 to the minus 4, so relative to each other, the high viscosity and at a low viscosity. So to be super clear, I'm showing here what we define as our high viscosity and low viscosity disk models and how alpha changes with radius. So for the bulk of the disk, and note that radius is shown here in log scale, alpha takes a value of either 10 to the minus 3 or 10 to the minus 4 outside of the dead zone. So because we are assuming that disk turbulence is driven solely by MRI, the turbulent alpha is directly linked to the electron fraction and so we reduce alpha by 2 orders of magnitude when the ohmic Alsacer number drops below unity, as it does inside the dead zone. One of the key tools that we use to understand how planetary growth and migration are intertwined is something called a torque map. So as a function of orbital radius and planet mass, we can visualize the magnitude and the direction of the torque exerted on a planet by the disk. So red regions here correspond to inward directed torques and blue to outward directed torques. So we're very interested in the conditions for outward torque. White regions correspond to planet traps, regions where a planet's migration is halted and subsequently its semi-major axis only changes if the planet trap itself moves inwards or outwards. So for planet masses that are above the gas gap opening mass, a planet will leave the type 1 migration regime. So we showed that here with the pink cross-hatching. The drop between the dead zone and the active zone is a consequence of the drop in alpha. And if you compare these two torque maps, you can see that there's also an overall shift downward in planet mass in the low viscosity case, and that's important. Over time, the torque map evolves, just as the disk evolves. So features in the torque map are determined by the disk's properties, and we can touch on each of them in turn using the low viscosity disk as an example. The outer edge of the dead zone, as we discussed before, is defined as the orbital radius where the ohmic Alsacer number exceeds unity. The water ice line is the location in the disk where the abundances of water, ice, and water vapor are equal, with of course more water being in the form of vapor closer to the star. Thirdly, the heat transition divides the disk into two regions according to the dominant heating mechanism, either viscous dissipation or stellar irradiation. Viscous dissipation dominates in the inner regions where the disk surface density is highest. So we get a smooth midplane temperature profile by adding the viscous and radiative temperature profiles as energy densities. So with a detailed understanding of the torque maps, we can now turn to our formation results, and I'll start with the high viscosity case. We overlay tracks of planet mass and semi-major axis onto the torque maps and compile each time step into a movie. So what you're seeing here, each black dot is a planet formed in its own separate simulation, and the gray lines display its growth and migration history. So we can watch what happens over the course of the simulation, and then we'll break it down. So if you've ever wondered what planet trapping at the water ice line looks like, this is it. We also see that planets escape the water ice line trap. But the key result I want to focus on in this talk is that for a high disk viscosity, alpha of 10 to the minus 3, we do not form massive planets at large orbital radii. And this is a consequence of the two barriers that I discussed earlier on. Higher viscosity leads to a depletion of the column density in the outer disk, and the torque on the planets in that region is entirely inward. The situation with a lower viscosity disk is different. And as I play the movie, focus on that same region of the torque map. So what you just saw is one of the key results of our paper. In the lower viscosity case, the column density in the outer regions remains higher, allowing sustained planet accretion. And crucially, the blue region of outward torque by the heat transition occurs at lower planet masses. So the combined effect is for planets that originally started out as close in as 30 AU to be drawn outwards to many tens of AU. They're then trapped at the region of zero net torque to slowly migrate inwards as the trap slowly moves inwards. If we focus on the state of the simulation at about 1 million years, approximately the current age of the HL-Tau system, we see that this group of planets have reached 1 to 3 Earth masses, and that they're currently trapped just outside the heat transition. The results I just showed you assumed an HL-Tau disk gas mass of 0.44 solar masses, but the outcome is similar for higher and lower mass disks. So under the assumption that the observed dust gaps in the HL-Tau disk are opened by planets, These planets are at the right locations to do it. The question then becomes, are they massive enough? Will a super-Earth mass planet induce a significant change in the pressure gradient? That is a question we leave to follow-up work. But in the meantime, we answer the question, why does the alpha parameter have such an effect on planet migration, and how can lowering it by a factor of 10 lead to planets being drawn outwards? The total torque experienced by a planet is a balance between, or sum of, the inward-directed Lindblad torque and the outward-directed co-rotation torque. So you can see that the mass dependence of the total torque is entirely driven by the mass dependence of the co-rotation torque. As a function of disk radius, there exists a planet mass for which the outward co-rotation torque will take its maximum. We're calling this planet mass MP corot, and I'm showing numerically calculated values here as black dots on top of the total torque map. So to be drawn outward, to have large semi-major axes, a planet simply needs to reach that mass. In our work, we dive into the theory, and we come out with a simple, working, analytic approximation for the planet mass at which the outward-directed co-rotation torque takes its maximum. The upshot is that MP corot scales like alpha to the 2/3. So a lower alpha results in a lower planet mass of maximum outward torque. Okay, thank you for listening. That's all I have time to share with you today. But to summarize, the two barriers to forming massive planets out at many tens of AU that exist for conventional values of disk viscosity are lowered if their natal disk's viscosity is lower than typically assumed. So planet growth, planet migration, and disk viscosity are intertwined.